Alright, in this video we're going to be taking a look at another related rate problem, this time involving distance between ships. So at noon, ship A sails from a dock at 10 miles per hour. Ship B is sailing west at 15 miles per hour and will reach the dock at 3 p.m. How fast will the distance between the two ships be changing at 2 p.m.? Okay, now that we've read the problem, our first key step in solving it is to locate any rates of change and express those as derivatives. So in this problem, it says that ship A is sailing north at 10 miles per hour. That 10 miles per hour is a rate of change. I'm going to express that as dA dt is equal to 10 miles per hour. Okay, ship B is also sailing. It's at 15 miles per hour. So I'm going to represent that as dB dt is equal to 15 miles per hour. And finally, the question in a related rate problem is always a rate of change as well. So how fast is the distance changing? I'm going to call that dz, z for distance, so dz dt, and that's our question in this one. Okay, so again, that is our first key step, is to locate the rate of change and just express them as derivatives and just write them down. Okay, after we found our rates of change, our next key step is to find a expression which relates together the variables that are changing. So in this case, A, B, and Z, the distance between the two ships. Now in this particular case, it's good to draw a picture. And when you're drawing a picture when things are changing, you really want the picture at the time that they're asking about. And here, they're asking about at 2 p.m. So we want to draw a picture of what this scenario is going to look like at 2 p.m. So we have a dock. I'm going to label that D. And then ship A sails north from the dock. It leaves at noon, and it's going 10 miles per hour. So at 2 p.m., how far along north will it have gone? Well, 2 times 10 miles per hour is 20 miles. So it will have gone 20 miles. But this side is still changing, so we want to put a variable there. I'll call it A. All right, now that we've figured out where ship A is, let's figure out where ship B is at 2 p.m. Well, it doesn't reach the dock until 3 p.m. and it's sailing west, which means at 2 p.m. it would still be east of the dock. Okay, so it'll be over here somewhere. Okay, and it takes 1 more hour from 2 p.m. to 3 p.m. for it reaching the dock, and it's going 15 miles per hour. So in that 1 hour, it has to travel 15 miles. Now that side is changing, so I need a variable there. So I'm going to call that B for the distance that B needs to go. Okay. Now you'll notice that B is decreasing as the ship sails towards the dock. So since that side is decreasing, I need to go back and change my rate of change. dB dt is not positive 15 because it's getting smaller. I need it to be negative 15 miles per hour. Okay, so now the final thing that we need is just the distance between these two ships, which is Z. I've already called it Z. Okay, and now I just need the relationship between A, B, and Z. And typically when we're doing distance problems, the relationship that you use is either going to be the distance formula if you're on an XY plane, or in this case, when we're talking about ships in the sea, we're going to use Pythagorean's theorem. So we have that Z squared is equal to A squared plus B squared. Okay? And that's our second key step, is to get a relationship between the variables which are changing in this problem. In this problem, it's A, B, and Z. Okay, now that I found the relationship between the variables that are changing in the problem, I'm going to take my third key step, and I'm going to take the derivative of this with respect to time. So d dt of this entire equation. All right. Now remember, when you're taking this derivative, you have to remember to use implicit differentiation, or the chain rule, and tack on your dz dt's, dA dt's, dB dt's. So in this case, it's just some power rules. The derivative z squared is 2z, and then we tack on our chain rule, dz dt. Okay. On the other side, we have 2a for the derivative of a squared, but we have to tack on dA dt. Again, anytime you take the derivative of a variable, you tack on the variable dt. Our last derivative is b squared, it becomes 2b, and then dB dt. Okay. All right, after we take in the derivative, all we need to do is plug in the given information and solve for the variable that it's asking for. Now the first thing I'm going to notice is that there's a bunch of 2's in this equation. I can divide both sides by 2 and cancel all those things out. Okay, now in order to solve this, I need to figure out what z is. Now the thing that can tell me what z is actually the thing that I differentiated in the first place. I know that z squared is equal to a squared plus b squared. So that means that z squared at 2 p.m. is equal to a squared. Well, a is 20, so 20 squared, plus b squared, and b at 2 p.m. is 15, so plus 15 squared. So z squared is equal to 20 squared plus 15 squared. If we do that arithmetic, we'll get z is equal to 25. All right, so now we can plug in everything that we know and solve. So z is 25, so 25 dz dt is equal to a is 20, dA dt is 10, plus b in this problem is 15 at 2 p.m., and dB dt is equal to negative 15. Okay, or we get 25 dz dt is equal to 200 minus 225 when we do this multiplication, or 25 dz dt is equal to negative 25. So that's a pretty easy division to do. dz dt is equal to negative 1, or 25 divided by 25, and the units on this is miles per hour for the distance. Okay, as always, thank you for watching this example, and if you like this video, please like and subscribe.